All right, there goes 1040. So that's my signal. You know what that means. Might as well get started. Let's see. So I don't have really any specific news about the second exam. I know the graders have gotten started, as have I. I figure this time we should have 3 moderately decent graders helping me, and I'm hoping at any rate that we can finish the grading like Monday, Tuesday, and maybe get them back to you in class on Wednesday. That's at least what I'm going to aim for. We'll do our best. I don't take anything for granted after last time, but I guess what this means is I'm hoping that we can do better on this exam than we did on the previous, which should not be all that difficult to do. It also occurs to me, I feel bad because I still have like 3/4 of the first exams left in my office. So what I'm going to try to do for Friday is to bring them to class again, the exam ones. And I don't know how many people will be coming to class, but if you do normally come in person, or if you sometimes do and sometimes don't and can for sure make it a point to come in person on Friday, I'm going to try to get you your first exams back to you. We're sort of stuck with this awkward situation, of course, because of the nature of this being a hybrid class, partly in person and partly online. So we'll do the best we can, but I would like to get them back to as many of you as I can. They do me no good sitting in my office. So I think that's about it for that. Again, I think in terms of OWL, you guys must have a bye week this week because we're not going to finish chapter 8 this week. So I guess that will be due next week, a week from Friday. Other than that, I can't think of anything really. Any really obvious administrative stuff I'm missing? Basically, today we're going to continue on in chapter 8. My goal is to cover these 2 reactions, halohydrin formation and also oxymercuration reduction. And you can see that I've left 4 whole lectures on chapter 8, and I don't mind taking them. I'm just as glad to go through this relatively slowly. And I do have a reef session for you guys today with actual polling questions. So that'll be the usual fare. It'll be 8 points just for attendance, just for participating, and then 1 point each for each of the 2 multiple choice questions. I'm still working on getting your reef app / reef website gradebook to look correct. I think I've made progress. I still don't think I quite have it right, but basically I would still say I'll continue to upload grades from time to time onto eCampus, and whatever you see on eCampus supersedes whatever you see in the reef app or reef website. Good. So just a reminder of where we left off before the exam. We talked about halogenation of alkenes. We said this is an addition reaction, or you could even say an electrophilic addition reaction. The electrophile in this case being the elemental halogen, Br2 or Cl2. And no wonder that this is an electrophile, or something that wants to accept an electron pair. By any means possible, halogen molecules would love to break that weak halogen-halogen bond. And remember, in terms of reaction energy, anytime we can break a weak bond and replace it with a stronger bond, that's money in the bank in terms of energy for us. So that's basically the driving force for that reaction. And you get vicinal or 1,2 dihalides of this type. We also talked about how in cases where there's a stereochemical issue, you can expect anti-addition, meaning that the 2 halogens will wind up trans to one another in the product. And we did examples of both types. But if we make a minor change to the whole thing and change the solvent from chloroform or dichloromethane or carbon tetrachloride to water, water can now react. Now, it's not a violent reaction. It's a well-controlled reaction, but water can react slowly with the intermediate and actually winds up getting incorporated into the molecule. At least the oxygen of water gets incorporated into the product. And you wind up with a species that looks like this. You can call that a vicinal halohydrin. Again, vicinal meaning that the carbon with the halogen and the carbon with the OH are next to each other. And so the OH comes from the water molecule. The hydrogen well, I don't know if I really should have said it. You get a molecule of HCl or HBr, because those are strong acids, right? Really what you'll get is X minus and H3O plus, right? Because that's a strong acid. That's going to dissociate. Not that we really care. This is an inorganic side product. We don't focus on those. You'll know whether you have to put it or not by how the question's phrased. You especially have to watch OWL carefully. They will sometimes want you to put really weird things for your products. I want us to focus on the major organic product. I think that's the thing we ought to be focusing on in an organic chemistry class. And so generally, unless the question specifically says to put the inorganic side products, generally we ignore them. But watch OWL carefully. They will sometimes say one thing and sometimes another. And actually, on the whole, I'm okay with that. I think it's good to get used to reading directions carefully. Can't tell you how many times when I'm kind of checking the OWL problems ahead of time of assigning them to you, I will get something wrong because I didn't read the directions. So I can totally relate with all that. So now not only is there a stereochemical issue, at least especially visible in cases where the alkene is cyclic like this one, there's also a regiochemical issue, because now we need to worry about which carbon gets the OH and which carbon gets the halogen. And you can see here, I'm answering that question. Effectively, the OH group is going to wind up on the more substituted carbon. And we defined the word substituted in an earlier class. And the halogen on the less substituted carbon. And that's not arbitrary. That's not a thing that you should just memorize. If you understand the mechanism, then you will automatically know everything you need to know about that. Because the reason the molecule winds up that way is because of the mechanism. So we're going to get into that next. And so I guess my plan is to at least go through the mechanisms of these two examples of halohydrin formations. Maybe then we'll switch gears and do our reef session. And then we'll go into the oxymercuration reduction reaction and what it's used for. And I guess if there's time left, I can do some more examples. That's kind of how I see the rest of this class going. Good. Any questions on the structures, or at least where we've gone so far, short of the mechanism? All right then. Well, let's first look at the reaction of one pentene. And so it might very well come as no surprise to you that the first step of this reaction is the same as if there were no water present, but an inert solvent like chloroform or dichloromethane. In the first step, one of these halogen atoms is going to add across the alkene. And again, you can draw these two arrows clockwise or counterclockwise. It doesn't matter. Basically, both of those bonds form at the same time. So I'm not sure, philosophically speaking, if there's even much of a difference between those two. And then, of course, don't forget to break that weak halogen-halogen bond. That's the main driving force of the whole reaction, and certainly of that first step. So at first, this looks just like the halogenation reaction. And you will get your cyclic halonium ion. Oh, I should at least write here Cl2H2O so we know what's going on. But now here comes the difference. Rather than a chloride ion, or halide ion in general, breaking that ring open, what does the job for us is a water molecule. And it will do the exact same thing as the halide ion would have done. That water molecule is going to add to the more substituted carbon atom. And the reason is that carbon atom is the one that has more plus charge on it. Really, the two carbon atoms in the three-membered ring are helping the chlorine to bear the plus charge. You could even draw resonance forms that show that. They would be very minor resonance contributors. But certainly the bulk of the plus charge is going to be on the halogen atom. Still, we've already talked about carbocation stability, and we said that the more substituted the carbocation, the more stable it is. And again, we've defined the word substituted before. So we would expect there would be more plus charge on the more substituted carbon than on the less substituted carbon. No wonder the electrons in the electron pairs in this oxygen are more attracted towards this carbon than towards the other. And it's for the exact same reason that if we didn't have water present, the halide ion would attack the more substituted carbon as well. The only thing is, in a halogenation reaction, there's no consequence to that, because both of those atoms wind up being attached to a halogen anyway. But here there's going to be consequences, because that's going to tell us which carbon is going to get attached to the oxygen. And it will always wind up being the more substituted carbon, no exceptions. That's always going to be the case with this reaction. Anyway, this also brings up other questions. Probably the first one that probably most, if not all of you are wondering, is how can I know that a water molecule will make the attack instead of a halide ion, because we still made a halide ion over here, didn't we? That's going to be one of the main questions I'll get asked. And the way you know that is as follows, and you need to know this in order to understand the reaction. I don't want you memorizing water just goes there because it does. There's a very good reason for it. And the reason is because water is the solvent. And that implies that it's there in a very, very large excess, probably 1,000 or 10,000 times as much as we would need for the reaction. Sure, we do generate a halide ion. That's still true. But you'll only generate one of those for every alkene molecule, whereas you might have 10,000 or 100,000 water molecules for every alkene molecule. So what you need to know is the reason that water attacks when you're given that water is present is because water is the solvent, and as such, it outnumbers the halide ions by several orders of magnitude. If you know that, then you will be able to remember why that's the case. Don't refuse to learn these things I tell you about why things happen. Don't just ignore it and try to memorize everything. Trust me, it will go much better for you if you understand why. And I think the reason why is fairly straightforward. Could you possibly redraw the arrows in the second step or explain that again? I'll do it really big. How's that sound? So you'll agree that water has these lone pairs. For the reasons we gave, the water is going to attack the more substituted carbon. And as a result, we'd better break a bond to this carbon. If we don't, then carbon will have 5 bonds. And so we break this bond and we put the electrons onto the chlorine. Don't focus on copying these arrows and memorizing that they look exactly like this, right? Al might give you a question where everything's flipped and the other side of the molecule, but you basically want to show one arrow that's showing the water molecule attacking the more substituted carbon, and another arrow showing the breaking of that bond. The reason we want to break that bond is twofold. One is because we don't want to have 5 bonds to carbon. That'd be a problem. And the other is this gets rid of the plus charge. So as a result, we have our chlorine attached here and our water molecule attached there. The reason I knew to draw this and to put a plus charge in oxygen is because oxygen starts out with 2 bonds to hydrogens, and so those hydrogens need to stay there. So that's the next intermediate that we get. This means that we're going to need one more step in order to get a neutral product. This species is not neutral, it's a cation. And in general, we want to get a neutral product as a result of the reaction. So that's another thing that you will need to know. In general, you're looking for a neutral organic product at the very end of things. So we need something to pull off that proton. And again, as I see it, when I look at what we're given, we've got a couple of choices. We could use a chloride ion, or we could use a water molecule. And again, I think the water molecule is the better choice for 2 reasons. One reason is exactly what we said earlier. There's many orders of magnitude more water molecules than there are chloride ions, or halide ions in general. And the other reason is chloride ion, Cl- is a terrible base. I can think of maybe one case next term where we're using halide ions as a base, not this term, next term. Because literally when we look at what's in the solution, there is no other choice. Here we have a much better choice. Water is a better base than halide ions. Why? Because halide ions are the conjugate bases of hydrohalic acids. HCl is an extremely strong acid, right? So, and you know that from Gen Chem. So what that means in terms of what you need to know is since HCl is a very strong acid, Cl minus is a very weak base. Likewise, HBr is a very strong acid. Br minus is a very weak base, a terrible base. So even if it weren't outnumbered, which it is, I think we'd be hard pressed to see any halide ions pulling the proton off. So we're going to use another water molecule, and we've got plenty of them. So we'll use one of the lone pairs in oxygen to pull off either of those protons. It doesn't matter which, they're the same. And then we break the oxygen-hydrogen bond, and this arrow shows the electrons in that bond going on to the oxygen and getting rid of the plus charge, and then you get your product. And again, I would expect that you would get a racemic mixture. Oops. Because this carbon over here is chiral. And so you'll know whether you need to show that or not based on how the question's phrased. Sometimes OWL will say, don't worry about stereochemistry. Sometimes it'll say, draw all possible stereoisomers. So that's how you'll know what you need to put. If it said, don't worry about stereochemistry, that answer's fine. So I'll go through that whole mechanism again before we attempt it with the cyclic one. The reaction starts with the halogen molecule adding across the alkene just the same as if we were doing a halogenation reaction. So you need to know the first step is identical for both reactions. And not surprising. If Cl2 and Br2 react with a carbon-carbon double bond so readily before, then they should do here. Question in chat, can you draw an example of a stereoisomer? If the question said that you needed to show all stereoisomers, then something like this would receive full credit. But if the question just said, don't worry about stereochemistry, just a flat structure like that is fine. Anyway, so the first step is the same. You have one of the two halogen atoms, which are of course identical, adding across the alkene double bond. These two arrows can go either clockwise or counterclockwise. I wouldn't even notice. You just want to show that you're forming a bond to one of the carbon atoms with one of these lone pairs in the halogen, which again could be chlorine or bromine. And then you're using the pi electrons to form a bond between the other carbon atom of the alkene and the same halogen atom. And then you also break the weak halogen-halogen bond. And remember, there is no issue of which of those three goes first. All of that happens at the same time. That's what we call a concerted step, spelled like concert ed. Concerted meaning it happens all at the same time. And so you get your cyclic halonium intermediate, just like before. Now, instead of a halide ion attacking in the more substituted position, a water molecule does, for reasons that we already stated. And you will need to know those reasons in order to understand this reaction adequately. The reason is that the water molecules outnumber the halide ions by several orders of magnitude, because water is the solvent, and you can tell that, you can know that based on what you're given. That's part of understanding what you're given means when you're given a reaction to work out. This means that water is the solvent. And so water will attack here. Now, let me get at another thing. I hope this doesn't muddy the waters too much. Some of you might say, how come I can't make OH minus do the attack? Because if I do that, then I'll go straight here and I'll save myself a step. This is something I've noticed in recent years. Students in general are very, very, very quick to notice things that will save them a step in the mechanism. And that's all well and good, except in general, these things that look like they will save you a step are counterfactual. They don't happen in real life. And so why can't you draw this? Why would you lose points if you drew this? You know, the simplest level I can answer that question on is because it's wrong, although that doesn't really help you any. Let me give you a slightly more helpful way of phrasing that. The way you know that you cannot use this is because we're not given it to begin with. You always want to look back at what you're given in an organic chemistry problem. And I don't see OH minus mentioned. I don't see NaOH, KOH, anything like that. Does that make sense? That's a really important skill. You always want to be looking back at what you're given. And you can't just make up species that would be convenient if they were there, but they aren't. So that's why we can't show that. That's why that would lose points. The reason we can't use OH minus is because there is none. And I actually don't know if the reaction would work under alkaline conditions. Maybe. I don't really have direct experience with this reaction. But that's a really important thing. That's something you're going to probably hear me say until we're all turning blue in the face, myself included, this term and next. Always look back at what you're given. And you need to use species in your mechanisms that make sense. So even though that would save us a step, it's counterfactual. It doesn't happen in real life. And the reason is because there is no OH minus to do that with. Well, I mean, yeah, you've got water, so what did you learn? That in neutral water, what? The concentration of H3O plus and the concentration of OH minus is what? 10 to the minus 7th molar each? That's negligible. You know, that's not going to be anywhere. There's probably fewer OH minuses than there are chloride ions, you know. It's much too few of them to make any sense to use them in a mechanism. That's a really important point, so I want to pause on that and make sure that makes sense. Any questions on that? And again, this is going on YouTube. You can, either in this class or the next one, you can watch me saying that 5 times if you want. I can't imagine that would be at all desirable, but maybe. Good. So once that attack of the water molecule occurs, again on the more substituted carbon, you've got this intermediate here, and we're almost done. We just need to show removal of one of those 2 protons, doesn't matter which, they're the same. And the only reasonable species to do that with, again, is a water molecule. And you'll wind up here with an H3O plus ion. You'll know if you need to put it or not based on how the question's phrased. You'll notice I didn't put it so you can draw your own conclusions. Why does the water molecule attacking and the OH bond breaking happen in 2 separate steps? That's another good question. You see here, the excellent question. See, here's another example of something that would save you a step. You see, students are very, very quick nowadays to perceive possible ways of saving them a step that they have to write down. And I'll have to answer on the same 2 levels. You know, the first answer and the unhelpful one is the reason you can't show that is because it's wrong. Again, doesn't do you a whole lot of good. Why is it wrong? Because in order to pull off the proton from the oxygen at the same time that it adds to the molecule, which I think is what the question's asking, you're asking 3 molecules to collide at once. You're asking another molecule to come in and pull off this proton at the exact same time that this species attacks the cyclic halonium ion. And the chances against that are just too high. That there's a severe entropic problem. It's hard enough, as you might know from Gen Chem, for 2 molecules to collide with the right energy and in the right orientation and all that to make a reaction occur. Asking for 3 molecules to do that is essentially next to impossible. So that's why you can't show that. That's why, let me say that more clearly, that's why you cannot show it that way. That way would lose points. So there's a good reason for it. So this reaction does take 1 more step than the halogenation reaction. But yes, so that's a second separate step that a water molecule will pick off the proton and you'll get your neutral product. And again, you'll know which way you have to show it based on how the question's phrased. Good, make sense? I'm hoping you guys can see some similarities with halogenation, but the difference is that you get when water is the solvent. And again, the main reason for that is water has this reactive oxygen atom that connect as a nucleophile. Chloroform and dichloromethane and molecules like that don't. There's no way those things can react irreversibly, but water can. Good, let's then go on and look at the other example. There we go. So we'll start over here with our methyl cyclohexene, and we'll add our bromine molecule first. Same as before. We form a bond between that halogen and one of the carbons using one of the lone pairs on the halogen, and we form the bond from the other carbon to that halogen atom using the pi electrons. And that can go either clockwise or counterclockwise. Not only will I not take off points, but I won't even notice, as long as you're clear about where the arrows are going. And we also break that halogen-halogen bond, which is weak. And breaking a weak bond and putting in their place some carbon-halogen bonds that are stronger is money in the bank. And you could then, in principle, draw either an enantiomer of the intermediate here. I think I'm going to draw this one, though, because I see that this one is the one that's going to wind up with this particular structure. And the way I know that is because of that carbon-halogen bond, which is going to be the same in that intermediate as in the product. So that's how I know to do that. But you'll know which you need to show based on what the product looks like. So we get this intermediate. It's at this point that our water molecule attacks, just like before. That's going to attack the more substituted carbon and break that carbon-halogen bond that breaks the three-membered ring and releases a lot of energy. In so doing, by the way, also gets rid of the plus charge in bromine. And when the water molecule comes in, it needs to come in from the opposite side. H2O comes from opposite side to three-membered ring. And the reason for that is the three-membered ring blocks it from coming from the same side, in this case coming from above. So the water molecule is going to come from behind, just like the halide ion did when we talked about halogenation the other day. And so as a result, when it does that, it's going to push this methyl group in this case so that it points up. It's going to come in from behind, push the methyl group up, and break that bond. Later on in chapter 11, we'll learn that's called an SN2 reaction. And so we'll have an actual name for that. But for now, I think that's all we really need to say. So in the end, our water molecule is going to point down. Our methyl group here is now going to be pointing up. This is an electron pair. And what else do we have? We've got this bromine over here. That's pointing up, and the way I know that is because this carbon-bromine bond is not involved in the reaction. The reaction happens all at the other carbon, not at this one. So that's how I know that. And then, of course, if you want to draw that hydrogen, you can. It's understood if you don't. So we will get this intermediate. And now all we need to show, just like we did before, is another water molecule coming in to pull off either of those two protons. And you will get the exact product we had before. This is now OH, hydrogen here, and bromine over here. Maybe I'll do this to show that we got rid of the plus charge on the halogen. And so you would also get the enantiomer. And remember how we defined enantiomers. What you would do is you would flip the stereochemistry on both carbons. So if you needed to draw the other enantiomer, which you would know by how the question's phrased, I would guess that would have OH here, and methyl group pointing down, then bromine pointing down, and hydrogen pointing up. That's not the only correct way to draw it. You could also have done it just by flipping the molecule over like this. So either way is fine. But you'll know which you need to show based on how the question's phrased. If it says draw both stereoisomers or all possible stereoisomers, then you'll draw all possible stereoisomers. If it doesn't, then you're probably fine just drawing one. Good, and that's basically it for halohydrin formation. And we took our time on that, but I don't really mind. Good, any questions on that mechanism then? And again, you'll be able to watch that as many times as you like on YouTube. Good. So, first question, which of the following cannot be made to undergo an addition reaction across a double bond? And of those 5 species, there's one that never gets any mention in chapter 8 as being possible to do an addition reaction. So maybe if I started it, that would help. But 4 of those things the chapter discusses as things that we can add across an alkene pi bond. The 5th one, there's no mention of it anywhere in the chapter as something you can have undergo in addition to an alkene. All right, last chance. Any others want to give a response? Going. Looks like we're holding pat at 82. Good. Well, I think C, D, and E are ones we know already pretty well. We know that halogens, both chlorine and bromine, can undergo an addition reaction across an alkene. We've been talking about that both today and whatever it was, Friday. Likewise, HBr and HCl and HI, we've known about those adding across alkenes since back in chapter 6 and 7. So that leaves just these 2, water and sodium hydroxide. Hopefully you know from glancing at the chapter that water can add across an alkene double bond. There is such a thing as a hydration reaction. The only one that's left is sodium hydroxide. There's no mention of that anywhere in your textbook as being something that can add across an alkene. So I think the best answer is B. You. Good. Next and final question. Which of the following could be the product of addition of Cl2 to an alkene? I think there is only one reasonable answer. All right, well, remember what we said in our discussion of halogenation of an alkene. We said that you get a vicinal dihalide or 1,2 dihalide. So your product should have 2 adjacent carbons, each with a halogen on it. And I see only one molecule that looks like that, which is E. B is only 1 halogen, so that's no good. C and A of the halogens both on the same carbon, we've seen nothing in terms of a reaction that can do that. And in D, you have 2 halogens, but they're not on adjacent carbons. So I think the best answer is E. Well, I do let me see which one you thought was the best answer. B. Oh, yeah, the reason that's wrong is there's only 1 halogen here. This could be the product of addition of HCl to an alkene. Absolutely. Well, even then I'm not sure, right? Because the chlorine would go on the more substituted carbon. So I think B is a number of problems with it. Does that help explain why E is a better answer than D? Because it says Cl2. Right? And, you know, it's just one question in one reef session all term. But that's fine. So your remaining points will come from attendance or participation. That's a good place to end. And so from here, I would like to go to your class notes because I've actually put all this down in your class notes. So let me close that off. We can also close this off. Good. So hopefully, oh wait, no. Well, yeah, we can end the reef session. That's fine. Not really ending the class, just the reef session. Good. So let me see if I can't make that a little bigger. Good. So what we're going to cover next is the various ways that we can add H2O across an alkene pi bond. Maybe I'll switch to the whiteboard just for a second, because we're going to learn a number of reactions that can do this for us, because there's various possibilities. But the idea is we want to be able to do the equivalent of adding water across a carbon-carbon pi bond to give an addition product that looks something like this. And there's multiple possibilities for that. And we're going to learn at least 3 different reactions. One we pretty much kind of know already, but the other 2 are going to be a good deal more useful for reasons that we will get to. So let's go back to the class notes, and I'm doing this because I already have the structures and mechanisms drawn in for you. So, like it says here, you can have alkenes undergo hydration, addition of water, just with aqueous acid, dilute aqueous acid. But there's a problem, which is if you were to treat this alkene, let us say, with dilute acid, you would not get the direct addition of water across it, not even the Markovnikov alcohol. And again, we went over Markovnikov's rule in chapter 7 that says the hydrogen would go on the less substituted carbon, and the other piece, whatever it is, in this case OH, will go on the more substituted carbon. But you're not even going to get this. You would wind up with this alcohol because it would undergo a carbocation rearrangement. So please do review that in chapter 7. That's a topic that we've covered. So what if we wanted to prevent that? Let's say we wanted to get the Markovnikov alcohol, but we wanted to lose all possibilities of a carbocation rearrangement. In other words, we want a mechanism that does not go through a carbocation. In that case, the reaction of choice is this one, oxymercuration reduction. And oxymercuration reduction takes 2 steps, and I really don't want you just memorizing all of these letters and numbers. Again, it will not go well for you. You need to understand what each of these things is and why it's there, and I've explained all that here in the class notes. So the main reagent that's going to do the job for us is mercury 2 acetate. So OAC is an abbreviation for acetate. This is the acetate ion. You could write this as ACO minus if you wanted to. It's the same thing. But mercury 2 acetate is 2 of these anions associated with a mercury 2 ion, Hg2+. THF and water are our solvents. THF, tetrahydrofuran, has this structure. It's a fairly commonly used ether solvent. One interesting thing about THF is it's pretty soluble in water, unlike most other ethers, and there's reasons for that we could get into. But that's why they're using aqueous THF here, is because you will get a homogeneous mixture this way. You won't get like 2 phases. So that's the structure of tetrahydrofuran. And that's the first step. And you also need to know what it means when you have steps numbered like this. Though you could actually just write, another way you'll see this written is mercury 2 acetate and aqueous THF with 1 arrow and then a second arrow that says sodium borohydride, NaBH4. That's another way of showing the same thing, to draw 2 separate arrows. Or if you just want to draw 1 arrow, then you need to number your steps. The reason you need to know this is that the numbered steps mean something. What it means is we're going to add our alkene to the solution that contains aqueous THF with mercury 2 acetate and wait until everything is done reacting, and then we will add the sodium borohydride. And part of what it means to know a reaction is to know details like that. Do I just toss everything in all at once, or does it take a couple of synthetic steps? And this is one that takes 2 synthetic steps. So we react our alkene with the mercury 2 acetate and aqueous THF, and we wait until the alkene's gone. There's ways of testing for that. You can do TLC or gas chromatography, something like this. And once your alkene is consumed, then you add sodium borohydride. And so as a result, you wind up getting the Markovnikov alcohol, meaning that the OH from water is going to be on the more substituted of the formerly alkene carbons, and the hydrogen on the less substituted carbon. But this way you will not get any carbocation rearrangement. And the reason you don't get any carbocation rearrangement is very simple. It's because there's no carbocation intermediate, as you'll see when we go over the mechanism, which is coming next. So I've listed out the structures of all of these things, and I will expect you guys to know all that. I am not above asking on an exam, draw sodium borohydride or draw acetic acid. You might even find questions like that in old exams of mine. I am not above doing that. I expect you guys to know these structures and not just to memorize letters and numbers. And the reason is if you know the structures, it helps you understand what's going on. There's too many little facts to memorize all of them, at least in my experience. Good, and I'm here explaining what the borohydride ion is for. We're going to use the borohydride ion as a source of H-, not H+, H-, the hydride ion. We're going to need that, as you see in the last step of our mechanism. So here is the mechanism of oxymercuration of that compound. And I basically am going to say here, everything shown needs to be shown. Anything not shown is okay not to show. So you can use this as your example mechanism. But that first step, boy, that looks an awful lot like adding the bromine or chlorine across an alkene, right? The only difference is we don't have this other bond to break. But basically, the mercury 2 ion is going to do the exact same thing as Br or Cl. It's just going to add across that alkene double bond, and instead of getting a cyclic halonium ion, you get a cyclic mercurinium ion. And so that looks something like this. In the next step, just like with halohydrin formation, our water molecule attacks the more hindered, the more substituted of the 2 carbons in the cyclic mercurinium ion. The way we know to use water is because we're given water, right? This step mentions water over here. So that's how we know we can use it. The water actually plays a role in addition to being a solvent, just like it did with forming a halohydrin. So the water is going to act as a nucleophile, attack the more substituted carbon, because that one's got more plus charge on it. The 2 carbon atoms do help the mercury atom to bear the plus charge, though I think most of the plus charge is in the mercury ion. But there's more of a buildup of plus charge on the more substituted carbon, so that's why the water molecule attacks there. And again, don't refuse to learn those things. They are the key to your success, is understanding these details about how these reactions work. Good, and in so doing, we break the carbon-mercury bond just like we broke the carbon-halogen bond. That breaks open the 3-membered ring, which releases a tremendous amount of energy. And also, what happens when we put these 2 electrons in the bond onto the mercury atom? Well, if you go back and look at the reaction we just did, you'll see that the halogen atom goes from a plus charge to neutral. The very same thing is going to happen here. It's going to reduce the charge on the mercury by 1. It goes from mercury 2 to mercury 1, and for the exact same reason as before. And then look at this step. You have water coming in and pulling off a proton to give yourself a neutral OH group, just exactly like with halohydrin formation. So these 2 steps, I would say, I feel like this is the first time I'm noticing this too, but these 2 steps are exactly analogous to what we just did in the halohydrin reaction. And so this intermediate actually is what's going to be swimming around very happily in your solution until you add sodium borohydride. And that's very important because we want to get rid of that carbon-mercury bond. We don't want there to be any mercury in our compound. That's stupidly toxic, as you're probably aware. So what happens is the borohydride ion, BH4-, releases H-. And I'm showing it like this, so everything shown needs to be shown. Anything not shown is okay not to show. And I explained that also up here when I drew the structures of all these things. So you can see here at the description of the structure of sodium borohydride that talks about how it is that we get that. Anyway, the hydride ion is now going to act as a nucleophile. It's going to attack the carbon that bears the bond to mercury and break that bond to mercury. Those electrons will then go on to the Hg+ ion and reduce it to 0, reduce it down to mercury metal. And so this carbon, in this case, will become CH3. So that carbon will gain 1 more hydrogen. That hydrogen will come from the sodium borohydride, and you get your neutral alcohol product. So from oxymercuration of an alkene, you will get the Markovnikov alcohol, meaning the one that you would get with OH being attached to the more substituted of the formerly alkene carbons, and the hydrogen going on to the less substituted of those carbons. But the great strength and importance of oxymercuration reduction is that you don't have to worry about carbocation rearrangements. And the reason that you don't have to worry about carbocation rearrangements is very simple. If you look at this mechanism, you won't find a carbocation anywhere. So the reason you don't need to worry about that happening is because there's no carbocation intermediate. Will hydride always attack the carbon-mercury bond? Yes, there are no exceptions. This step will always involve the hydride ion attacking the carbon that bears Hg+. There are no exceptions. It always happens like that. It may not be exactly here, you know, the molecule may be turned around and look very different, but it's certainly always going to be that carbon that the hydride ion always attacks. And so you get your Markovnikov alcohol without having to worry about the possibility of carbocation rearrangements. Good, we're doing very well for time. Any other questions then? And I have here some more tips for you. So I'll just end with this, since we're essentially already out of time. I have like 30 seconds. What if you wanted to make the non-Markovnikov alcohol? In other words, what if you wanted to make the compound that would result from adding water across an alkene double bond, but such that the OH goes to the less substituted carbon and the hydrogen to the more substituted carbon? Sometimes they call this the anti-Markovnikov alcohol. I'm not a fan of that name, because it makes it sound like this reaction is an exception or somehow breaking the rule. It's not. There's a very good reason why you get the non-Markovnikov alcohol. And just as with all of these other reactions, it comes directly out of the mechanism of the reaction. So that's what we're going to start with next time, is our hydroboration oxidation. So other than that, and again, a reminder, I'll try my best to remember to bring your exam ones to class on Friday. So please, as many as possible, please come get your first exam. Other than that, have a great day. We'll see you Friday.